Fantastic, thank you. So I'm very happy to be here for this event. You guys have had a very long, productive, fun day, I hope. And so I'm gonna round it out by talking about privacy. So for this talk, I will not assume any familiarity with like a differential privacy. I of course assume you guys have some like, math background, learning theory background. But I think that like privacy has been a topic that is sort of like generally in the knowledge frame of kind of interest. Privacy is important. We have to figure out privacy. I'm sorry, my dog is whining because there's a dog barking in the hallway. And so although privacy is sort of like commonly agreed to be important, I think not everyone is as familiar with some of the like technical foundations. And so that's what we're going to like talk about in this talk today, differential privacy foundations and applications. And it's really going to be, what is differential privacy? What is the definition? What are some algorithms we can use to achieve it? What are some open questions? Because I think it's really important, as I assume many of you guys are kind of like embarking upon your research journey. I want to also arm you with some like types of questions that are really interesting to think about in hopes of giving you guidance and some inspiration there. So in that case, without further ado, let's talk about what is differential privacy. So this is a formal privacy notion that was defined back in 2006 by like Dwork, McSherry, Seaman Smith. And then pictures, it says this. Imagine if I have some database containing data from some people, and I plug that into my favorite randomized algorithm, then I'm going to receive as outputs something sampled from the following PDF here. Like in this case, I'm going to have kind of like all possible outputs on this x-axis, and then here on the y-axis, I'm going to have what is the probability or the likelihood that I output a particular thing as a result of running this algorithm instantiated on this particular input. Good. And so this is like the PDF of the output of a randomized algorithm. And a privacy notion is going to be, imagine if I were to change one person's data, say that I change Alice into Javier, and I plug this new database that is the same except for one person's data into my same algorithm, and I'm going to get out a different PDF. And our privacy constraint is going to require that these curves are not too different. And this is going to be formalized by a constraint on the ratio pointwise between these two curves. And so now, like, how does this translate into privacy intuitively? It seems like I'm bounding ratios of PDFs of some algorithm. Like, how does this work? Well, so now imagine that an algorithm produced this thing, and then some adversary tried to make an inference. Do we produce this particular output as a result of having Alice's data, like as a result of having Javier's? And so this adversary wouldn't be able to make any meaningful inference beyond the amount specified in this bound on the ratio between these two cases. And so this is the kind of idea. Formally in math, it says this. We'll say that some algorithm M, the maps from like an n tuple of data. Think of this as being like data coming from n people into some arbitrary output range R. And so this is more than just reals, but it's some range R, is going to be parameterized epsilon delta differentially private if it is the case that for all neighboring databases, D and D prime, that are the same except for one person's data, and for all possible things I may produce as a result of this analysis, I'm going to produce that thing with about the same probability under these two neighboring databases used as the input to my algorithm. And this notion of being like about the same is going to be parameterized by these two privacy parameters. And the first and perhaps most important is the epsilon. And so kind of like this is our bound on the ratio. And you'll note that our like a parameter epsilon appears in the exponent. And so this means you really want these things to be small because even a large epsilon is going to be like exponentially large in terms of the boundary ratios. And so you want this epsilon to be small. And this is your kind of like primary privacy parameter. And then you also have a delta here, and this gives you some kind of additive slack. And this is really helpful. For example, if you have a probability 0 event, then you can't have anything besides a kind of infinite epsilon. And so this kind of enables those cases. And you want this delta to be very, very small because you are bounding a probability. And so if your delta is 1, it's basically meaningless. And so you really want this delta to be very, very small so that you are giving some kind of meaningful bounds on these probabilities. And so effectively, this is saying we're going to bound the kind of a maximum amount one person's data, can change the output. Only we're talking about the distribution over outputs, not necessarily the kind of realization of the output. And so this is helpful to think about in this kind of neighboring database paradigm, where maybe this is the world with your data, and this is the world without your data. Or maybe this is the world in which you are truthful when you provide data, and this is the world in which you lie when you provide data. And we're saying that kind of no matter what things you are worried about happening, whatever collection of bad outcomes you might be concerned about, those bad outcomes are going to happen with about the same probability, whether or not I see your data. And so this is helpful because if you're thinking about what's the probability New York Times reporters come to my house based on my search history, well, that's probably pretty low if they don't see your data. And then it will continue to remain low after they do see your data. On the other hand, something like insurance prices rising as a result of a medical research study finding a causal link between smoking and lung cancer. Well, if you're a smoker, there's a good chance that your insurance premiums are going to rise, whether or not they see your data, because they are learning from the population and not from you personally, because this is a population level fact. And so this is a quote taken from the differential privacy textbook. It's by Dwork and Roth from 2014. And it says that differential privacy addresses the paradox of learning nothing about an individual while still learning useful information about a population. And so this says we can still learn smoking causes cancer. We can't learn about your particular health record. And importantly, it's a definition, not an algorithm. And so this doesn't say how do we achieve differential privacy. It just says this is a property that an algorithm may or may not have for certain epsilon values. So let's.
Rachel? Sorry, yeah. There was a quick question in the chat. I thought now would be a good time to answer it. So the question is, does the adversary know how B and B prime are different? And if not, why does it matter if the PDFs are different?
Excellent question. So in fact, this holds for all neighboring databases. And so this isn't just for some fixed example where I change one person's data, but this is saying for all possible databases you might have, and for all possible people who you might want to consider changing their data, and for all possible values of data they might have instead, this will hold for kind of all of those simultaneously. And so in fact, it's very, very strong. And importantly, we assume nothing about the adversary's knowledge or their computational power. And in fact, this is a kind of information theoretic guarantee. And so we're saying, regardless of what the adversary knows or their computational abilities, we're still going to protect against them and kind of any inferences that are made.
Thank you, Rachel.
Yeah, sure. So we're now going to move to kind of talking about the algorithms that can achieve this. And I think this will also help to clarify where do these PDFs come from, is we're really saying here, I want to find an algorithm that will satisfy these particular properties, but kind of in the differential privacy literature, we do have kind of a number of tools that will have this automatically, and they're in fact designed for that. So the first one is the Laplace mechanism. And this was like defined in the original differential privacy paper, the same one. So it's kind of no surprise that it is like a differential private because it was their example of an algorithm that M is. And before we can talk about the algorithm, we have to talk about a property of a function that we will call sensitivity. And so recall that like a differential privacy wants to hide changes caused by one person's data. And so this is going to measure how much change can be caused by one person in the worst case. And so this is the sensitivity of some function f. And importantly, we're going to be looking at like a real valued functions for now. On the next slide, we will think in a more broad sense, but at least on this slide, we're going to be talking about real valued functions. And so we will like denote this delta f. And this is going to be defined as a kind of like maximum absolute difference of the function value when evaluated on kind of two neighboring databases that are the same except for one person's data. And so you're going to think, what is it like maximum change one person's data can like cause in this? As an example, let's think that we're computing the mean of bits and I have n people and they each have a bit. Well, then you can think in the worst case, changing kind of like one person's bit, maybe from a 0 to a 1, will change this value 1 over n. And so in that case, the delta f would equal 1 over n. However, of course, you can think of like, lots of other functions. They're going to have lots of other sensitivity values. And so this is a way of making this fully general. And so given this, here's what the Laplace mechanism does. It's very, very simple. So we just take in our like database function value and our privacy parameter. We first just like compute the true answer, and then we add noise. What type of noise? Laplace noise, hence its name. And Laplace is not a distribution that is particularly common in many other applications, but it is very common in like a differential privacy because it works so well with a privacy requirement. It's basically like a two-sided exponential with mean 0. And its tails are going to have an exactly exponential decay rate. And so that's what these pictures are. Over here, ignore the green one because we don't do that. And this like a parameter inside is going to really tell us how kind of concentrated or how dispersed should our noise be. And so having a smaller parameter value here is going to lead like to more concentrated noise. Things are going to be closer to 0 with higher probability. And so therefore I'm going to be adding less noise. On the other hand, if I have a large parameter value, then I'm going to be adding like a pretty spread out noise. And this is going to add more noise in my analysis. And so translating this back into this internal parameter. So we know that if I have a smaller parameter value here, it means I'm going to add less noise. And when would that happen? So that would happen either if I have a pretty small sensitivity, meaning that I don't have to hide very large things. If I'm only looking to hide small changes, then I can add small noise. Alternatively, if my epsilon is large, and so recall our like a privacy definition, smaller epsilons corresponded to like a stronger privacy. And so on the other hand, if I have a larger epsilon, then my constraint is going to bind less often, and then it can add smaller noise for a kind of weaker privacy guarantee. And so these are the two things that really go on, and we will continue to see this ratio sensitivity over epsilon because in fact this really is a sort of like key point. One more common mechanism is what's known as the exponential mechanism, and this was defined by McSherry and Talwar back in 2010. And this one is used for kind of non-numeric queries. So before we saw the kind of, as we defined delta F, it had to be like a real valued query. But now we can think about questions like, what's the most common eye color in the room? I can't say like blue plus 0.3. And so instead we have to find a way to kind of like translate these into kind of like not necessarily numeric outputs. And so the exponential mechanism is going to assign a numeric quality score that will take as input database and the output range, and it will map that to a real number. And it will then, using those quality scores, is going to sample outputs based on pace. And so you can interpret this as saying like, Q taking in X and R is a quality of kind of outcome R for a particular database X. And so back to our example, what's the most common eye color in the room? If we have a bunch of like brown-eyed people in the room, then I would say brown should be a like high quality on this particular database, and blue, which is less popular, should be considered lower quality with respect to the ground truth of this database. And so then we're kind of like working with the exponential mechanism, you really have to, in defining this like this kind of like quality score, you really have to think about what is the goal of my analysis? How do I assign goodness numbers to my possible things I may produce compared to like the ground truth of my database? And that requires some kind of like, domain knowledge or kind of like broader like, problem understanding. And so then using this, we can return to our approach of defining sensitivity. Only now we're going to like define it for our score function, because I can now say numerically, what is the worst case change in this function between two neighboring databases if I were to change one person's data? And importantly, I'm going to look at the max overall neighboring databases X and Y, but I'm not necessarily going to look at all neighboring outputs, because there isn't a notion of kind of like neighboring outputs, changing one person's data relating to a different output, but instead I want to look at like the worst case over all possible outputs of this change in neighboring databases to the quality score. And so then with this, I can then define the exponential mechanism that will take in a kind of database X, a quality score describing the qualities of the things I may want to like output in my privacy parameter epsilon. And I'm then just going to sample something R with probability proportional to kind of e to the power epsilon times the quality over 2 delta Q. And so again, we have this ratio of the privacy parameter and the like sensitivity that appears again here, and we now have to have a couple like normalizing factors. So we're doing something kind of like sampling with exponential bias towards things that have good like outcomes. And so intuitively, you might think exponential and the quality score would achieve that. We have to make sure that we incorporate this kind of other term, sensitivity over privacy parameter, in a way that we ensure the sampling probability meets a privacy requirement.
Rachel, I think we're getting a few questions about the choice of metric induced to the score function.
Sure.
So I'm going to try and summarize a few of these in one. Can we use a different metric between f of d and f of d prime, where I guess f is still qualitative, like it's like outcome mapping to outcome R? And following up on that, is there any intuition behind why people don't use other metrics like KL divergence or Wasserstein as different metrics?
I'll have you read the chat for me, because it's hard to have the chat open and this.
Sure.
What do you mean metrics? Do you mean for this quality score?
Yes, on the quality score, or maybe a different choice, maybe something that directly is a metric in the qualitative space.
Yeah, good. So really here is where you want to use some sort of nuance and some kind of like a domain knowledge, and there's no single right answer for how to pick a quality score, but there are some properties that you want to achieve. One is that kind of like possible outcomes that are closer to your ground truth should receive higher scores with respect to your database. And then you also want this to be kind of like smoothly gradiated. And so you don't just want it to be the correct answer has quality 1,000,000 and then kind of everything else is going to have quality 0. So like, back to our example of like, the most common eye color. Let's say that I have a database that has like, 15 brown eyes, 14 green eyes, and one blue eye. So then I wouldn't just want to say brown is 1, blue and green are going to have quality 0, but I might want it to be what fraction of the database has that particular eye color. That's a common one if you're doing like, counting queries. Like if you're doing something more complicated, it might be, so you can in fact use this to do kind of like numerical queries. We are considering a kind of like arbitrary rate range here, but it can be real valued, in which case you might want to say, what is the like, absolute real difference between kind of R and the value of my function on my true database. You can also use this for kind of like numeric examples where just having like additive accuracy doesn't make sense, in particular in the kind of like economics application of like pricing. So we know if you want to maximize revenue, then you have to pick a price. But if you price a little bit too high, all of a sudden you're going to get 0 revenue because the price will be too high, and at that point no one will buy. But if you price a little bit too low, then it's fine, and then you're going to get like approximately the same revenue. And so this is also like another application where like I don't just want to say like compute the optimal price and then kind of like perturb it a little bit, because in that case, if you perturb it up, you might get 0, and that's bad. So this is like a really general framework, and you can think about how do you want to instantiate this in the context of the problem for which you are applying this algorithm. And so there's less one single right answer and more kind of what are your goals in the application of this, and then choose the quality score appropriately.
Great, thank you.
Yeah. Excellent questions, you guys. Keep them coming. So one final algorithm that I want to talk about, because it's like important and it's simple, is what's called randomized response. And this was, as you can see from its site, this has been used long before differential privacy came around. And this was used originally in kind of like a behavioral literature to kind of get people to provide true answers to very embarrassing questions. For example, do you have a particular disease that may be embarrassing? You don't just want to be like, yes, definitely. And so this gives people an answer, a way in which they can feel as if they have privacy, even when they are responding directly to a person. And it's very simple, and its name kind of indicates how it works. So you're going to flip a coin. If it's tails, be truthful. If it's heads, give a random response, possibly through another coin flip or some other randomization mechanism. So it's very, very simple. And this is helpful for kind of directly asking embarrassing binary questions where we can talk about coin flips. Things have been used in practice for kind of non-binary responses and even higher dimensional ones. For example, translate a person's information into a bit string, hash it so that it's lower dimensional, do something complicated to correlate coin flips across the kind of bits in their hash, and then you can still And then you can still kind of like reverse engineer this like accurately. But the crux of it is we're just like flipping coins and like sometimes being truthful and sometimes being random. And so in this case, each person's response is kind of noisy, but it's biased towards the truth. And so if you have enough of these observations and you know the noise distribution, then you can still like reverse engineer inference. So these are the three most commonly used private mechanisms. I'm now going to talk about a couple properties of the differential privacy definition that we like, that make it very nice in terms of kind of like algorithmic properties. And the first is that it's robust to post-processing. And so this says, if I have an algorithm M, and it's epsilon differentially private. In fact, this holds for delta too. If it is epsilon differentially private, and if I have any function that I want to compute on it, and so think of A as being like an adversary, well, then the kind of adversary applied to the output of the algorithm is still going to be epsilon differentially private. And so this says no adversary can break the privacy guarantee. And so this is important. For example, if you want to publish things in the world, you want to make sure no kind of computationally bounded or even computationally unbounded adversary can break your privacy guarantee. That's important. And we now know that can't happen. And again, kind of returning to an earlier question, but the adversary and their knowledge, this is completely independent of the adversary, of their knowledge, of their experience, of their computational ability. And so this is in fact a very, very strong guarantee. One more thing is what's known as composition. And so this says, as I perform more and more differentially private computations on my data set, then my privacy parameter epsilon is going to degrade gracefully. And this is one, as it's stated, it currently only applies for the epsilons, but in fact it holds also for the deltas. And so this says, if I want to run k different algorithms on my data, each of them are going to be epsilon I differentially private for the ith round. And if I were to just kind of run them all in a row, then that whole process is going to be differentially private with the parameter is just the sum of my epsilons. And so this says my epsilons just kind of add up. And so that's very, very simple. We can in fact do a stronger but less pretty version. And this is what's known as advanced composition. And so this says, if I have a k-fold adaptive composition of some differentially private algorithms, and this k-fold adaptive means that I'm going to k times in a row. I'm going to first pick an algorithm, run it, see the answer, and then use that answer as an input to my next algorithm, possibly even using it to decide the next algorithm I can use. And so there's a lot of adaptivity here. So if I do this k times, then it's still going to be a differentially private. And I'll kind of point out the key parameters because this one is less pretty, but is more tight in terms of its bounds. So in terms of the delta, I get a k delta and I get a little extra amount here. And my epsilon, I get something that looks like square root k times epsilon. And we sort of ignore these terms in our big O. It turns out this one is going to be small. In our big O, we don't care about twos. And we do have a small cost in our epsilon for this kind of additional delta thing. We can say at a high level, we get roughly square root k times epsilon. And this is nice because before it would be k, and now it's square root k. And so we're saying that we're going to improve the bound in our epsilon at a small cost in our delta. And I know that I'm close to time, and so I'm gonna wrap up by talking about a few other practical considerations in this space. And the first one is kind of who adds noise. And And I have, in fact, implicitly, like I'm giving you guys the answer to this is that it depends. And there's two different models. And the first one is what's known as a trusted curator model. And so this requires, for example, in the case of the Laplace mechanism, everyone has to hand over their data to some curator who's going to see it all exactly. And so this is why it requires trust. And then they're going to compute on it, and they're going to publish something with some noise. On the other hand, we have the local model, which is what we saw in the randomized response example, which kind of happens if we don't actually trust like the analyst to see the raw data. We're going to add noise to our own data before we hand it over. And so there's some pros and cons of these models. In the local model, you also get privacy kind of from the analyst, and so that's nice, but you're also adding much more error because you have to add noise independently for each person, whereas in the trusted curator model, you can sort of coordinate the noise, and that's going to lead to kind of much more accuracy. And so the question is what can we do privately? And the answer is a lot. In the past 15 years, we have seen many private algorithms developed, and this is only just a tiny sampling. So we now have a lot of algorithms for a lot of important problems in the space of machine learning, statistics, optimization, and so on. And so I want to close by kind of pointing out differential privacy. We have seen it has a diverse algorithmic toolkits, and it has been used a lot. It's being now deployed in practice by kind of several major tech companies as well as the federal government. And it's kind of always achieved by injecting noise somewhere in the analysis that will scale with this ratio delta F over epsilon. And the kind of algorithm design questions are going to be, how do I add this noise and where in a way that kind of won't harm meaningful accuracy of my analysis? And so you might be wondering, what makes a DP research question interesting? Because it kind of seemed on my last slide that we have a bunch of algorithms for a bunch of problems. It seems like it's a solved field, and I guarantee you it's not. And there's kind of many interesting things here. But they typically fall into three categories. One of them is solving new problems with existing tools. And so maybe you work on typically a very particular type of learning theory question, and maybe that hasn't ever been done privately. I mean, the field only existed for 15 years, and so we haven't solved all the problems yet. And you might think, I want to solve this problem. Maybe I can use the exponential mechanism, and that kind of would be interesting. Another interesting approach is developing new tools. And the fact that we have post-processing and composition means we only need a small number of kind of private building blocks, and perhaps then we can use those to build more complicated algorithms. And so if you want to build a new tool, a new building block, that would certainly be kind of used a lot. And then third is kind of helping deploy these things in practice. And usually this involves something non-trivial. And so it's more than just, I coded up the Laplace algorithm, hit, compile, and it was done. But there's usually something meaningful, interesting happening in that space. So I will close there, and I'm very happy to take any questions.
Wonderful. Thank you so much, Rachel, for a great introductory talk to DP. Yeah. I'm going to leave a minute if anybody else wants to type in more questions, but I'll ask one question that did come up at the end. Is there any connection between DP and causally informed prediction, where inferred causal structure can predict which unit is receiving treatment, etc.?
This is a great question, and in fact, one that I have started thinking about this year. So I can tell you there is certainly a connection, but it's not fully explored in the literature. And this is definitely like, solving a new problem with existing tools. We used and this joint work with my student Seong Ro, who maybe is here, maybe is not, they haven't checked in the like participant list, and we use a kind of like Laplace mechanism. And so this is like existing basic tools to kind of like design like differential private algorithms for doing synthetic control, which is the type of like causal inference. So that like falls into this category. I don't have a good answer as to the connection in general, but I can just say we wrote one paper, and there are certainly many more future papers that can be written on this space. I think especially because the field of like causality is getting like very, very hot. I think there is certainly a lot of interest in like combining privacy and like causality.
Awesome. Thank you, Rachel.